When we look at something like these very complex looking patterns, we might get the idea that there's actually quite a lot going on behind the scenes to generate those patterns, when in reality the rules for those patterns to emerge are quite simple. So let's look at those rules, and I call them complexity out of simplicity. Let's call this algorithm intersector or intersections, and it goes like this. Let's have a look at only these two lines that we created here. And each of those lines consists of a static point, the blue one here, that does not move, and a dynamic, a moving point here, the orange one, with these red arrows here indicating the direction and the magnitude of motion. So each orange point will be moved this direction and this distance in each step of our simulation. So after our first step, not much has happened. Both lines just got longer. This one just from here to there, and this from here to there. However, the next step is more interesting, because the lower line here will be intersecting the diagonal here. And what we do in this case is we use the intersection as the orange point's new position, and not the position that this point would have if we just moved it for the length of this red arrow and ignored the intersection. And also, we're going to deactivate this point, so it cannot move anymore. So we end up with something like this static, non-moving line after it intersected another line. But we also create a new line here, or on a randomly chosen point along this now deactivated line. And the direction of the new line we create will be perpendicular to the direction of the deactivated line here. And maybe we use a random number generator to determine on which side of that line the new line will be generated. In our case, this is the new line that we just created, and this here is its direction of movement. And that's all there is to this algorithm. As you can clearly see, this line will be intersecting this line here somewhere, and we will again spawn a new perpendicular line to the old deactivated line now. And it's these two rules, deactivate a line if it intersects another line, and create a new line perpendicular to the deactivated line, that are solely responsible for these complex patterns to emerge. So to build this in Houdini, let's drop down a GeoNode, dive in there, delete the file, and drop down a circle instead. And we're going to use this circle, orientated along the XY plane, to scatter some points that we're going to use as initial points for our lines. And let's just have 200 points in here. Like this. Next, let's create the actual lines and also set their moving and static points, so the orange and the blue points in our diagram, as well as the moving direction. Going to use a pointer angle for that, and for each of those points we want to create another point. So we're going to create an integer, call it new pt for new point, and use the add point function to add a new point with the same geometry stream and the current point's position. Like this. So when we middle mouse on this, we can see we got 400 points, whereas before we only had 200. Next, let's create and set a point group for these newly created points, which will be our moving points. So use the command set point group of our zero geometry. That's the geometry we're currently working on. And the point group should be called moving. And let's set it for our new PT to 1, like this. Middle mouse on this, and we can see we have now 200 out of those 400 points in the group called moving. So we'll only have one end of the line in that moving group. Next, let's create the actual line by calling the add prim function. And to our current geometry, we want to add a polyline. That's just a line. And we want to add our current point at ptnum and our new point, new pt, to that line as its endpoints. Middle mouse on this again, and we can now see 400 points, 200 primitives. Also, if we enable the prim numbers here, we can see those primitives have been created. Next, let's drop down another pointer angle and initialize the direction of those moving points. So up here, we only select the moving points, and for those we're going to set a vector attribute called dir for direction. We're going to set it to, let's use a random number generator for now. Plus 1, 2, 3 here is just meant as a seed, so you can dial in the random values a bit. And let's also multiply this by 2, 2, 0, and subtract from it 1, 1, and 0. What that does is, on the one hand, it scales down our z-axis, so the direction can only be in the xy plane, and on the other hand, it remaps it from -1 to +1, so our direction vector can point in any given direction along the x and y axis, but not on the z-axis, which is always set to 0. Let's just add a visualizer here, and we are gonna visualize a vector. I'll show the arrow tips, and the vector we're going to visualize is called dir for direction. Let's file this in and highlight it, and we can see now these are the directions in which my points will be moved. Also for later, what I want to store is the start position. So let's create another vector called start pause and set it to our current position, which is our starting pause. Middle mouse on this to check. Yep, it's there. And what we'd also like to store as an attribute on our points is the primitive number that the points belong to. So what we're going to use is an integer called prims, and this will be an array. And we're going to use the pointPrims function, which will take in our geostream and our current point number, and we'll spit out a list of primitives that this point belongs to. And we know that it only belongs to one primitive, so our prim should be the first entry of that prims list. And we're just going to store that in an attribute called source, like this. Okay, let's have a look at the geo spreadsheet. Okay, that's working. So that's all the preparation work we had to do. Again, we created a bunch of points randomly scattered on a plane, or a circle in our case, and then created a few attributes on them. A direction in which they should move, a group, which only encompasses half of those points. Then we used point pairs from the moving and the non-moving group to generate lines. And finally, we stored the start position of that line, the original position of that line, on the moving points, as well as the primitive number of each respective line. We also stored that on the moving points. So now that we've done this, we can take care of the solver and what's happening inside of the solver. So what I want to do is, on the one hand, I need a subsolver, which will execute this thing over and over again for each frame. On the other hand, I will need a point wrangle that I'll put into the solver. And the way I like to develop this stuff is just have the point wrangle outside the solver, and when I feel it's almost there or I feel confident it'll work, then put it inside of the solver and test it there. So we will develop outside of the solver for now. So what we want to do for each step of the simulation is we only want to take into account the moving points. So let's just select this here. And we need to have some variables set up before we dive into the code. On the one hand, I want to dial in how quickly those points move. So let's call this amp for amplitude. It'll be a float. And we want to dial it in with this float slider here. Like this, create the slider, and we can see we have our amplitude now. Set it to 0.05 maybe for now. So what we can do now is, just for the sake of testing, is each moving point's position is equal to its previous position plus our directional vector, like this. And it does not take into account the amp, of course, because I haven't multiplied it with that, like this. That's better. Okay. So now I'm driving basically the step width for each simulation step. Let's get rid of that for now, because what we want to do in essence is we want to check if with the next step a given line will intersect another line that's already there. And if it is, then we will stop the line, we will create a new line, etc. And if it is not intersecting, we will just do this position plus equals direction thing that we just saw. So we'll just move the line further. In order to check for intersections, there are different functions here. And the two that Vex ships with are called intersect and intersect all. And when we go to the help page of those functions, we can see the intersect function computes the first intersection of a ray with the geometry. So a line can be regarded as a ray, and the other lines can be regarded as geometry. So in essence, this does what we need. However, what's not explicitly written here is that we cannot set up the precision with which this function calculates the intersection. In contrast to the intersect all function that's linked up here, we can set the tolerance, that means the precision with which we will calculate those intersections. And it's for this and only for this fact that in this setup, with lots of experimentation and lots of cursing and lots of bug fixing, I found out that it's better to use the intersect all function, although it's a bit more complicated to call. In this case, it's really worth it. Intersect all needs, on the one hand, the geometry that it should work on, no problem. It can take in a string to include or exclude certain parts of the geometry for that intersection analysis. It needs a vector where the line that should be checked for intersections is coming from. It needs the direction of this line, so where is it going and how far is it going? And then it'll spit out the intersection position, the intersecting primitive number, and a UV coordinate of the intersection. And also we can dial in the tolerance, so how precisely we want those intersections to be calculated. Okay, when you read a help file for Vex and Houdini, you can sometimes see these yellow ends in front of a variable name, which means that the function will actually modify those variables that you pipe in here. So it'll store the results into those variables. And these square brackets indicate that they should be arrays. So what we'll have to do is create those 3 arrays first in order to store some return values in them. Let's call them hit pause, hit prim, and hit UV. So we just took care of those 3 here. We can set the tolerances directly, so we don't need to take care of that. We know the geometry, that's 0, the current geometry we're working on. The group, however, is interesting. Because what happens when I create this new line here, intersect all will also report this here as an intersection, which is something that I don't want. Because if, as soon as I create my new line with a length of 0, it's already intersecting another line, it'll never grow. Because I'm just checking for line-line intersections. And if 2 lines intersect, I will stop one of those lines. This newly created line would never get the chance of actually growing somewhere. So what I'll have to do is I will have to exclude the source primitive, that is, the primitive number of the line from which the new line is being created. I have to exclude that primitive from my intersection analysis. So I'll only look out for intersections other than with my parent line, so to speak. And we'll have to formulate that into a string to use it as the function's group parameter. So let's create a string, call it grp for group, and it should be equal to an exclamation mark, and I set that in quotation marks to tell Vex it's a string, and the exclamation mark means not. So the group should not be the parent, the source primitive of this whole thing. And if you remember, up here we stored an attribute called source with the primitive number of that line. So let's do that and add to it the attribute source. However, this will give some error here, as Houdini cannot combine a string like this here with an integer number here. We have to convert this integer number into a string first with the help of the function called I2A. Okay, so now I'm only getting the error message down here where I didn't complete the function call. So now I think we're all set up to call the intersect underscore all function. So it takes in our current geometry, 0, then our group. Then let's look at the help again, the original position of my line and the direction. And when I look at this picture in my diagram, I can see that in our case, the moving point's position would be the origin and the vector with the direction stored would be the direction. So our origin is just v at p, my current moving point's position, and the direction is v at dir for direction. Then it spits out hit pause, hit prim, and hit UV, and it also takes into tolerance attributes. Let's set one to 0.01 and the other one to -1. So the first attribute is the general tolerance, that means the precision with which we detect intersections, and the second one is an attribute to tell Houdini if it should merge intersections within a given radius, and we don't want that, so we set it to -1 as explained here in the help. Also, we want to store the number of intersections, so how many intersections did we find, 0, 1, 2, 3, and we can just store that directly in an integer called intersects, and intersect all will return the number of intersections into this variable here. Okay, what didn't I check? Let's just open up the help page one more time. So geometry is 0, string group, vector origin, vector direction. Of course, the hit prim is no vector, it's an integer, like this. Okay, so now all we're doing is we test each of those steps if they intersect with another line on that plane that is not my parent line. So let's check if we found a hit. So if intersects is bigger than 0, let's first set our moving point's position to the intersection position. So v at p equals hit pause, and we just want the first hit that we get. We don't care for the other ones. Again, we are just using intersect all here because we can dial in the precision. So we're only just caring for the first intersection that we find. And also, if we hit something, we want to deactivate the growth of our line. So we're going to set our group moving to 0, like this. And if we didn't find intersections, so else, we're just going to use our position and increment it by our direction like we did previously. Just multiply it with our amplitude, so we can dial in the step size down here. And also up here, we want to take into account our amplitude, as this influences how far we check for collisions. Okay, this is the really basic setup. Let's just save this and just copy this point wrangle, go into our solver, paste that point wrangle here and wire it up to our previous frame, and then go up one level, highlight the solver, and hit play. And we can see this is our first iteration. And it's kind of working okay, because apparently it stops when it hits something. You can see, as soon as a line hits another line, its growth just stops. And maybe we can dial in the precision a bit better. So let's set the precision to 0.001. Let this run again. Yeah, that's better. Next, let's dive into the solver and create those new lines after we stop the old line. And for that, if you remember the diagram, we want to randomly choose one point on this now deactivated line. For that, we're going to use a function called lerp, linear interpolation, that does spit out any position between those two endpoints, depending on a value called bias, which goes from 0 on the one end to 1 on the other end. So what we're first going to do is create a float called bias, and it should be a random number. I'm just going to use the nrandom function to generate it, which spits out a random number between 0 and 1. Next, I'm going to generate the new line's starting position. It's going to be a vector called new pause, and I'm going to use the lerp function, linear interpolation, and I want to interpolate between my current position, v at p, and also my start pause. Let's see if I called it start pause. Yeah. And I want to use the bias to generate the new value. Okay, that is just the origin position of my new line that I'm going to spawn here. So let's create the line's first point. Call it npt1 for new point 1. And we want to add a point at our new pause. Also, we want to set this point's point group to 0. So it's the static point. Let's take a note here. Next, we need to generate the direction of that new line. And remember, we want it to be perpendicular to the just deactivated line. And a neat trick that we can use to generate a perpendicular line to that line is to use the cross product of the direction of my now deactivated line and an up vector. In our case, the up vector will be along the z-axis, so sticking out of that plane here, to generate a vector that is perpendicular to the direction of my old deactivated line. Let's call this one ndir for new direction, and it should be equal to the cross product of the normalized. That means its length should be 1, the normalized version of my direction, and an up vector sticking out along the z-axis, so 0, 0, 1. And of course, this should not be an integer, but a vector, like this. Next, let's randomly flip this vector, so let's randomly choose if it sticks out on the one side or the other side of our deactivated line. So let's just check if our random generator is bigger than 0.5, and if it is so, let's just take ndir and multiply by -1, like this. So we'll just flip it on the other side, just scale it. Now, again, we want to find out which is my parent's primitive number, and if you remember, let's go up one level here. We used these two lines here to determine that, so let's just copy those, head back into our solver and into our vex. We're just going to find the parent line's primitive number. Let's call it nprim for new primitive numbers like this. So again, what we're doing with those two lines is just we're looking at the primitive number of that line from which we just spawned the new line and then store it in this variable called nprim here. So and now that we have all these variables set up, we can add a second point here. And this one should be moving. So let's create a new point, npt2. Let's add it at the same position as our first point. Then set some point attributes. For example, source, which should be the number stored in nprim. Let's just copy this here, paste it. So we want to set the direction as well, stored in our variable called ender. And let's set the start position as well, which is our new pause. And finally, let's just copy this here and set our point group moving to 1. So this point here is now in the moving group. And finally, after we did all this, let's just create the new line by just adding primitive, in our case a polyline, using npt1 and npt2 as their respective endpoints. Okay, fingers crossed. Let's save this, head up one level, and hit play. And we can see now that seems to be working, and it also seems to be getting really, really slow. So let's zoom in a bit and see what's going on there. For example, this here. I mean, this is really tiny, but still, we are trying to find intersections, we are generating new lines, even if they are in these really tiny areas that we might not really care about. So what we could do inside of our solver here, inside the point triangle, is before we create this new line here, if we caught an intersection, let's check if the line that just intersected something, so the line that just got deactivated, if this is still above a certain length or if it's already too small to care about and to spawn a new line from it. So let's check if the distance between our current position and our start position is bigger than a value coming in through a slider. Let's call the slider min length. And if it is so, let's do all this. And also indent this properly. And create our float slider for the minimum length. Set it to 0.02, go up one level, and hit play. We can see now on the one hand this is miles faster, on the other hand it does not generate as many details. So that's already working. And what I like to do, I mean, diving in there, dialing in the values, going up again is a bit tedious, so let's just crank out the parameter interface here on our solver, and then dive into our setup here, and then just drag our amplitude slider and our minimum length slider up here. Hit apply and accept. Also, let's go up one level again, zoom out a bit, and hit play again. And we can see those lines out here, they keep on growing pretty much forever, resulting in this starburst look. So what I might do in order to dial in this effect a bit better is also generate a maximum length slider that those lines can have. So just checking if they are past the maximum length. So inside of the solver again, and in our point triangle, if we didn't find any intersection before we move this line's endpoint, let's check if, again, the distance between current active point and our start position, if this distance is bigger than a float value coming in through a float slider, let's call it max length, and create that float slider, set it to 3 maybe. So if that distance is, if it is below our maximum length, we still move it, and if it is not, so else, we don't move it anymore, but instead set the group underscore moving to 0, just to denote this line is dead. Okay, let's expose that again on our solver, so up one level, go to edit parameter interface, and then go back into the solver, and just drag this max length parameter up here, hit apply, and accept, and go up one level again. So now we have some measure to control the maximum length my lines can get. So again, hit play, and we can see those lines stop after they reached a certain length. So this is the basic setup. Let's delete this one and this one, which were just there for development reasons, and we end up with a setup that's basically 5 nodes. Let's talk a bit more about what was involved when coming up with this setup. So just let me crank out the editor here, hitting Alt-E. so we get a better overview of the code. So when developing this setup, and it might not look like much, there were two major hurdles that I had to take. On the one hand, realizing that only with intersect all could I dial in how precise I want the intersection analysis to be. I tried at least 2 evenings to figure out why my intersections weren't working correctly when using intersect only. And just by accident I stumbled upon this feature of intersect all. So I guess there's no general wisdom involved here, it's just trying to be persistent, trying to find out what the actual bug is, going through your code line by line and trying to eliminate errors there, and then again reading through the documentation of your functions in order to be able to figure out what is going wrong. And overall, I think kind of a gut feeling helps sometimes, because in the end it was nothing more than a gut feeling that was pointing me towards intersect all as a culprit for the situation. The second hurdle I encountered when coming up with the setup was excluding a line's parent from the intersection, so what we do here with the grouping. Using this grouping function and generating the group with this expression here might be straightforward, absolutely. However, it took me a while to figure out how to correctly assign a parent primitive number to a newly generated line. And in the end, the realization came that it's just those 2 lines that I had already written when setting up the whole setup before my solver. This is one of those kind of logical twists and logical knots that sometimes form in your head when you're trying to come up with a setup. And in this case, it helped me to actually break down the setup and just manually write down on a piece of paper the steps involved in that setup to actually work. So what do we need to do after we have an intersection, and how do I find out, or what is the right primitive number as a parent number for a line? So my hint there would be, if you get stuck, again, it's about persistence in a way. Don't get frustrated too easily. Just try and bite yourself into that problem. Just like a nasty dog you can't shake. If anything else fails, just step away from the code for a while and try to calm down and logically analyze the steps that you're taking, and try to logically explain why they need to be taken in that order, or if there is anything wrong in your logic, in your reasoning. This is one of the major aspects maybe of developing setups. Finding persistence and calmness to actually go through the steps of your setups, even when being away from the code and from a computer. With that, I hope you're having fun with this one. Looking forward to seeing lots of cool artworks from you guys. Just a hint, the initial line direction is one of the major features driving the look of the resulting lines here. So again, have fun and see you in 2 weeks. Cheers!